In this lecture, we shall discuss how to use vectors in order to solve problems in 3D geometry. We will begin with the definition of a basis of a space. Definition. A basis of space is a set of three vectors u, v, and w such that when they are drawn with a common starting point, so that is if u is AB, V is AC, and W is AD, the 4 points A, B, C, and D do not lie in the same plane. So let us illustrate this with the following picture. So here you should imagine that this is a three-dimensional picture. And so here we have three vectors with a common starting point. And these three vectors form the shape of a tetrahedron, so that these 4 points do not lie in the same plane. Using Euclid's axioms for spatial geometry, it is possible to prove that the basis, as we defined it, has the following two properties. One, every vector in space can be expressed as a linear combination of basis vectors. So if we have any vector S, then we can find scalars C1, C2, and C3 such that S can be written as C1 times U plus C2 times V plus C3 times W for some scalars C1, C2, C3, which are real numbers. And the second property of a basis is equally important and says that if a linear combination of basis vectors is equal to zero vector, so that is C1U plus C2V plus C3W is equal to 0, then all three scalars must be 0. C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0. These are the two fundamental properties of a basis, and they will be indisposable when we solve problems in vector geometry. Let's consider the following problem. We have a tetrahedron ABCD. In this tetrahedron, we pick M to be the midpoint of the edge AB and consider a plane MCD that slices through this tetrahedron. Also, we construct a point P, which is the point of intersection of medians in the base BCD, and then join this point P with a line through A. And we let Q be the point of intersection of the line AP with the plane MCD. What we need to find is we need to find the ratio in which the plane MCD cuts the line AP. So that is, we need to find the ratio of AQ to AP. The first thing to do is to construct a basis. And the convenient basis associated with this tetrahedron would be the following. So we can take U to be AB, V to be AC, and W AD. So here we have these three vectors, U, V, and W. Next step is to take interesting vectors and express them as linear combinations of the basis vectors. Well, let's start with the vector bk. So we use head-to-tail rule, and we can write bk as bc plus ck. Now, I forgot to tell you about the point k. So k is the midpoint of CD, and we need it so that we have a median bk in the base here. And so here we have, so BC we can further decompose as BA plus AC, and CK, so because K is the midpoint of CD, so this can be written as 1/2 CD. So then we do the same thing for CD. So what we have is, so BA can be written as minus AB plus AC plus 1/2 CA plus AD. And now we can relate this to basis vectors. So minus AB is minus U, AC is equal to V, and we have 1/2 CA is negative V, and AD is W. And combining this together, we get negative U plus 1/2 V plus 1/2 W. The next vector we want to consider is the vector BP. And to express this vector, we use the fact that the point of intersection of medians cuts them in proportion 2:1. So if we consider the median BK in the base BCD, then we can write that BP is 2/3 of BK. And BK is obtained here. So what we get is minus 2/3 U plus 1/3 V and plus 1/3 W. Next, we express vector AP. AP can be written as AB plus BP. Now, AB is just the vector U, and the expression for BP is here. So if we put this together, then we get 1/3 U plus 1/3 V plus 1/3 W. The next two vectors that are interesting for us are those associated with the plane MCD. So here we're interested in finding the expression for MC and MD. So let's start with MC. In order to express MC as a linear combination of basis vectors, we apply head-to-tail rule passing through the point A. So we write this as MA plus AC. And then MA is 1/2 of BA, because M is the midpoint of AB. And we have plus AC. And so what we get is BA is negative U, so we get minus 1/2 U plus V. We deal with MD in exactly the same way. So MD is MA plus AD, and we're going to get minus 1/2 U plus W. For the next step, we go from three-dimensional geometry to two-dimensional geometry. And we just consider the plane MCD. So here, the point Q belongs to this plane. So the vector MQ will lie in this plane as well. And what we can say is we can choose this pair of vectors MC and MD as a basis of plane MCD. And now, since the vector MQ lies in this plane, so we can say MQ lies in MCD, because of this, we can express MQ as a linear combination of basis vectors of this plane. But we don't know the coefficients of this linear combination, so we're going to write it with unknowns. So we're going to write MQ as X times MC plus Y times MD. And finally, so if we denote by Z the ratio that we need to find, so here the vectors, so the vector AQ is a multiple of a vector AP. And so what we can write is, we can write AQ as Z times the vector AP. Now, in our preparation steps, so we expressed all vectors that appear in this right-hand side as linear combinations of U, V, and W. And so now the thing to do is we want to tie together vectors MQ and AQ using a head-to-tail rule. And so one way of doing this is the following. So we can write that AM plus MQ is equal to AQ. Let us now take this equality and substitute for these vectors our expressions in terms of U, V, and W. We begin with the left-hand side. AM is 1/2 U plus MQ. MQ is X times MC plus Y times MD. So we have X times MC, and here is the expression for MC, minus 1/2 U plus V, plus Y times MD, which is minus 1/2 U plus W. And this equals to AQ, which is Z times AP, and here is the expression for AP, 1/3 U plus 1/3 V plus 1/3 W. In our next step, we're going to move the right-hand side to the left, and we're going to combine all terms with U, with V, and with W. So now, so we'll have the terms with U plus the terms with V plus the terms with w. So for u, we have 1/2 minus, so here we have x over 2 minus y over 2, and here we'll have minus z over 3. Now the terms with v, so here we have x, there is no v here, and here we will have minus z over 3. And for the terms with w, so we're going to have y minus z over 3. And since we moved everything to the left-hand side, so this is all equal to the 0 vector. Now we apply our principle. So we have a linear combination of basis vectors, which is equal to the 0 vector. So from what we said earlier, so this means that we can equate each coefficient of this linear combination to 0. So we get the following system of linear equations. Since this is such a simple system, I'm not going to bother with matrices and Gaussian elimination. So here we can easily analyze it, and from the second equation we see that x is equal to z over 3, and from the last equation we see that y is equal to z over 3. Now if we substitute these two expressions in the first equation, and then we're going to get 1/2 minus z over 6 minus z over 6 minus z over 3 is equal to 0. So now moving z terms to the right-hand side, we get 1/2 is equal to 2z over 3, and expressing z from here, we get that z is equal to 3/4. And this is exactly what the quantity that we seek. So here we need to find the ratio of AQ to AP, and what we see is that this ratio is 3/4. So this means that the point Q splits AP in proportion 3:1. Let's consider another problem on geometry of solids. So here we have a parallelepiped ABCD EFGH. So a parallelepiped is a three-dimensional generalization of a parallelogram. And let's choose K, a midpoint on AE, and consider the plane BCK. And also consider the diagonal AG in this parallelepiped. And we choose the point Q to be the point of intersection of the line AG with the plane BCK. What we want to determine is we want to determine the ratio in which this point Q cuts the diagonal AG. So we want to find AQ over AG. The first thing to do when we solve these problems is fixing a basis. And here we will choose the following basis. As vector u, we will choose AB. As v, we choose AE. And as w, we choose AD. Since we have a parallelepiped, here we have lots of equal vectors. And the vector AB, for example, is equal to the vector DC, and it's equal to the vector EF, and is equal to the vector HG. So all of these vectors are equal to U. Now, let us start expressing some interesting vectors in terms of our basis vectors. So the first interesting vector is the diagonal. So what is AG? So here we can use head-to-tail rule, and we can write this as AB plus BF plus FG. And so AB is our U. Right? So AE is V, but So what we have is BF is equal to AE. So this is vector V. And the vector GF is equal to the vector AD, which is our W. And what we get is that the diagonal AG is equal to U plus V plus W. The next pair of interesting vectors are those that are associated with the plane BCK. So here we can write that BK is equal to BA plus AK. Now, BA is negative AB, and AK, since K is the midpoint of AE, so this is 1/2 of AE. And this becomes negative U plus 1/2 V. And we have another vector, BC. But this vector is equal to AD. And so this is just W. For the next step, we restrict our attention to the plane BCK. And we choose this pair of vectors that we have here, BK and BC, as a basis in plane BCK. Then any vector that lies in this plane can be expressed as a linear combination of these basis vectors. In particular, the vector BQ lies in the plane BCK. And hence, we can write BQ as a linear combination of BK and BC. Only because we don't know the coefficients of this linear combination, we use the unknowns. We'll write X times BK plus Y times BC. Next, let us look at the line AG. So the point Q belongs to this line. And so if we denote this ratio by Z, so then we can express AQ as a constant multiple of AG in the following way. So we can write that AQ is Z times AG. As a next step, we're going to connect vectors AQ and BQ through head-to-tail rule. And we can do it in the following way. We can say that AB plus BQ is equal to AQ. And now let us start putting everything together. So we're going to substitute here our expressions for all these vectors in terms of basis vectors. Well, AB is simply equal to U plus BQ. So BQ is X times BK plus Y times BC. So we have X times BK, and here is the expression for BK, minus U plus 1/2 V plus Y times BC. So this is Y times W. And this is equal to AQ, which is Z times AG. And AG is U plus V plus W. Next, let us move everything to the left-hand side and collect the terms with U, with V, and with W. So the contribution for U, 1 from here. So from here we get minus X. And from here we get minus Z. Terms with V. Here we get 1/2, or we get X over 2. No V here, minus Z. And terms with W, we're going to get Y minus Z. And this is all equal to the 0 vector. And now we apply our fundamental principle. If a linear combination of basis vectors is equal to 0 vector, then all coefficients of this linear combination must be equal to 0. And we get the following system of equations. We get 1 minus x minus z is 0, x over 2 minus z is 0, and y minus z is equal to 0. So from here, from the last equation, we get that y is equal to z. From this equation, we get that x is equal to 2z. And finally, if we substitute this in the first equation, we get 1 minus 2z minus z is equal to 0. So this tells us that 3z is equal to 1, and z is equal to 1/3. So this tells us that the point Q splits the segment AG in proportion 1 to 2.